I'm going to start off today with, it's really a bit of a digression, really. I'm just showing you something that I always enjoy. So the digression is to talk about things called Pythagorean triples. So a Pythagorean triple is a triple, A, B, C, of positive integers satisfying the equation a squared plus b squared equals c squared. Of course, the name is because that would be a right angle triangle. So A, B, and C would be the sides of a right angle triangle, and so you're looking for right angle triangles with integer sides. So you probably know some examples like the 3, 4, 5 triangle, or the 5, 12, 13 triangle. Those are the two smallest Pythagorean triples that are interesting. So the question is how to find them all. So let me see. The best way to do this, the trick is to divide by c squared, and so you get the equation actually that a over c squared plus b over c squared equals 1, or x squared plus y squared equals 1, where x is a over c and y is b over c. And the observation is that because a and c are integers, that's a fraction. It's a rational number. It's in the field Q of rational numbers, and similarly y is a rational number. And so in this way you see that an equivalent problem to finding all Pythagorean triples is to find points x, y. So I thought that I should call these rational points. Right, so points x, y, not in R2 as you're probably used to, but in Q2, lying on the unit circle. Right, so lying on the unit circle, that's this equation here, x squared plus y squared equals 1. So finding Pythagorean triples is really, after dividing by c squared in this way, it's really just the same problem as finding rational points on the unit circle. For example, I don't know, 3/5, 4/5. That's a rational point on the unit circle, or 5/13, 12/13. Right, so these rational points on the unit circle, those would correspond to those Pythagorean triples under this little trick of dividing by c squared. So given your rational point on the unit circle, you just scale up by the common denominator and you get a Pythagorean triple and vice versa. And the thing is, we know how to do this. Using the trick we just saw. Remember that which came from our substitution. That was what we were doing last time. I was telling you about this crazy substitution, t equals tan theta over 2. And so let's just recall that story a little tiny bit. So we had this picture. We had a unit circle. And we had this idea that we should look at a point on the unit circle. So let me see, we had a picture something like this, didn't we? So that was a general point, x, y, a point on the unit circle. And and we realized that if we call that intercept t, so we joined it up to this point this point at -1, 0, and looked at that y-axis intercept, we found that x was equal to 1 minus t squared over 1 plus t squared, and y was equal to 2t over 1 plus t squared. The way I said it last time we saw this was that was angle theta, and that was angle theta over 2, and t was tan theta over 2. So we kind of got to that equation. And you can turn this around. If you know x and y, what's t? So if we know the coordinates x, y of that point on the unit circle, how would you find that y coordinate t? Well, there's some similar triangles here. So t is that height. So the ratio, that height over that width, that's t over 1, is going to be the same as that ratio in this bigger similar triangle, which is that's y, and that is 1 plus x. So t is y over 1 plus x. Right, so having a point on the unit circle, so that means x squared plus y squared equals 1. You can convert x and y into this number t on the y-axis by using t equals y over 1 plus x. And if you know t, you can recover x and y using these two formulas. So we have a function from the y-axis to the set of all points in R2 on the unit circle. So points with x squared plus y squared equals 1. And you remember that we couldn't quite get that special point on the left there when x is minus 1. So I've got to remove that point. So this function sends t to the point x, y. And there's a function back in the other direction, taking point x, y in that set, so on the unit circle, to y over 1 plus x. You see right there why it's pretty important that x is not equal to minus 1, because I can't divide by 0. So actually we have a pair of functions going in each direction here, and these are mutual inverses. Right, so this forward function and this backward function, if you do one after the other, it's the identity. So these are two-sided inverses of each other. So they are what are called bijections. You might be used to the word one-to-one correspondence. They're mutually inverse bijections. In this way, you can use this set, the y-axis in this case, to parameterize the points in this set via this formula. And now we observe that if actually, so I'm not going to put r there, I'm going to put q there, put the rational numbers, and I'm going to put q2 there, rational points on the unit circle. And the thing is, if you start with t being a rational number and you go forwards with this forward function, if t is a fraction, t is a rational number, well, this guy here's a rational number, and this guy here's a rational number. So you go from rationals to a rational point. And conversely, if you've got a rational point on the unit circle, so x and y are rational numbers, then y over 1 plus x is a rational number. So these actually give you bijections between the rational numbers and the rational points on the unit circle. Thus, we see that q parameterizes these rational points on the unit circle. Hence, the Pythagorean triples. So that's kind of a beautiful classical geometric application of this weird function that we saw from last time, coming from our substitution t equals tan theta over 2. So let's just finish with a couple of examples, because there's not really much more to be said. This is just a nice thing if you've never seen it. If you take like t equals a half and you apply this rule, what rational point on the unit circle do you get? You get the point 1 minus a quarter over 1 plus a quarter, that's 3/4 over 5/4, that's 3/5. 4/5. Okay, so that corresponded to the Pythagorean triple 3, 4, 5. Or if you take t equals 2/3, I think when you plug that in, you get 5/13, 12/13, which is that next easiest Pythagorean triple, the 5, 12, 13 triangle. Or if you take maybe, what's next? Maybe t equals 3/4. And I think if you plug that in, you get the 7, 24, 25 triangle, another Pythagorean triple. So that's kind of fun. Okay, now let's get back to work. That was a digression to just something that's kind of neat if you've never seen it, and there's not much more to be said. Okay, so now for the main topic this week. So I want to talk about how you should define those classical functions that we've talked about a lot and used a lot. So what's actually the proper way to define them, the proper mathematical way to introduce these functions, right? So this is things like the natural log and the exponential function or the trig functions. I'm actually going to talk later on this week about the hyperbolic functions, which you may or may not have seen before. There was a little bit about them on last week's homework, actually. So let's start off with natural log and exponential, because they're kind of the easiest to explain the point of view. We've talked about these before. So you've certainly seen them, but let me see. We had the natural log function and the exponential function. So these were inverses of each other. I'm just thinking about everything we know. We have done quite a lot with them, so I'm not really trying to tell you all of the properties. You know all of these things. You know all your laws of logs and your laws of exponents. And let me see, you know things like how to define like a to the power x. So here a is any positive real number and x is any real number. I think when I talked about these right at the beginning of the course, I explained how it was not so easy to define exponents a to the power x when x is an irrational number. And so the way you do this is if you know the exponential function, then a is e to the natural log a, and then all to the power x, so it's e to the x ln a. So once you've defined the natural log and the exponential function, you can define more general powers, a to the power x for any real number x. So this becomes the definition of these more general exponents. So although I've used these functions a lot and all their properties and you've probably seen these for many, many years, I didn't ever attempt to explain how to define exponential and log functions properly mathematically. And so that's what I want to sort of go to do. And then later this week, I'll do the same for the trig functions and introduce these hyperbolic functions. So there's various ways to go about this. Maybe the first approach is worth doing. So for this, you actually start with natural log x, and you know, of course, that the natural log of x is the integral from 1 to x, 1 over t dt. So this becomes the definition. So what's going on here, I'm using the fundamental theorem of calculus in its theoretical form. This 1 over t is a continuous function, and the fundamental theorem of calculus, the first way we stated it, says that any continuous function is integrable So you can define this new area function, integral from 1 to x, 1 over t dt, and then the fundamental theorem of calculus tells you that that area function is differentiable. And the derivative of that area function is the function you started with. So this gives a... So this is just two applications of that theoretical form of the fundamental theorem of calculus. So the idea here is you're not meant to know a function natural log at all. You don't know any such function that's an antiderivative for 1 over x. But this area function gives you such a function. So you take that to be the definition of natural log, and you get a good definition of a new function which is differentiable with derivative 1 over x. And you add that function to your toolkit of functions. So this is an excellent way to proceed, and it gives you the natural log function. And then let me see, as 1 over x is greater than 0, for x greater than 0, the natural log function is increasing. It's got positive slope everywhere. And if you're increasing, then you're 1 to 1. And if you're 1 to 1, you're invertible. And then you define the function e to the x to be the inverse function. Okay, so this introduces natural log. This becomes the definition of natural log. It's defined to be this definite integral which exists by the fundamental theorem of calculus. And then that function is invertible, and you define the exponential function e to the x to be the inverse function. Okay, so this is a very good way to proceed. Let's see if we can prove some properties. From these definitions. You don't just want, when you're trying to set up these functions rigorously mathematically, you don't just want the definition, but your definition has got to be good so that you can derive all the properties of those functions from your definition. So let me see. We have that the derivative of ln x is 1 over x. That was from the very beginning because that was what the fundamental theorem of calculus gave us. What about the derivative of e to the x? So how would you do this? You would let y equal e to the x, which remember by definition is the inverse function of natural log. And then you would differentiate both sides with respect to x. And so that, well, d by dxing is the same as d by dying times dy by dx by the chain rule. And d by dy of ln y is 1 over y. So that would give you that dy by dx is y, which is e to the x. Okay, so that proves that the derivative of e to the x is e to the x. So here is this nice function, the exponential function, whose derivative is itself. Great, so that's one property. What else do you want? You want laws of log. So how do you get the log laws from this definition? So that's things like natural log of AB is natural log of A plus natural log of B. Natural log of A to the B is B natural log of A. Okay, those are the two basic laws of logarithms that we want. So let's see if we can prove those from our definition. So here's my attempt to prove this. So for the first one, so what have we got to I'm trying to prove this formula. And I've got to use the definition of natural log. This is the definition. So to prove that, what do we need to show? Well, by the definition, we need to show the left-hand side, well, that's the integral from 1 to ab, 1 over t dt is equal to the right-hand side, which by definition is the integral from 1 to a, 1 over t dt, plus the integral from 1 to b, 1 over t dt. So what I'm going to do is I'm going to take the right-hand side. So that's integral from, so this is often what you do when you're trying to prove an identity. You take the most complicated looking side, which is the right-hand side, and you manipulate it until you get the left-hand side. So I'm going to leave the integral from 1 to a, 1 over t dt the way it is. And here I'm going to let u equal at. I'm going to do a substitution. So if u is at, du is a dt, so dt is 1 over a du. I'm just doing the substitution. 1 over t is a over u. I'm just making this substitution, and then these were t limits, so I need to go to u limits. When t is 1, u is a, and when t is b, u is ab. Okay, but then that a cancels and that a cancels. And look, that's integral from 1 to a, 1 over t dt. And here I've got the integral from a to ab, 1 over u du. I may as well go back to using t's because that's just a dummy variable. And now you see that these limits, area from 1 to a and area from a to ab, you can just merge them together, is going from 1 to ab, 1 over t dt, and there's a u that got out of place. Let's sneak that back to being a t like it was meant to be, and that is the left-hand side. Okay, so that's checked, that identity. I think I can just prove the other one quite easily as well. That's the other law of exponents that you're used to, right? So how would you prove that? Well, I've got a to the power b. All you have to do is remember the definition of a to the power b. It's e to the power b ln a. That was the definition of what a to the power b even means. And now I've got a natural log after an e to the power, and they're inverse functions, so that's b ln a, so that second one somehow is easy. It's just the definitions, more or less. Okay, so now we've got a great definition of natural log. We're defining natural log as this integral. We've got a somewhat indirect definition of the exponential function as the inverse of the natural log function. We've proved derivative of natural log is 1 over, and derivative of e to the x is e to the x. And I've just proved the laws of log. Let's see, what else do we need? We'd like the laws of exponents, wouldn't we? And then you're kind of in business, right? Everything's set up in this theory. So this is not too bad. What do we want? We want e to the a plus b is e to the a, e to the b. And what's the other one? E to the a to the b is e to the ab. Those will do. Let's just prove those laws where the base is just the number e. Once you've got the laws of exponents when the base is e, you can extend to get the laws of exponents when you have an arbitrary base using the definition of what that means. So again, I'm going to prove these guys quickly for you. So for the first one, let's see, what shall I do? I think I'll take I think I want to take the left-hand side, which is, I guess I should follow my philosophy, and I should start with the most complicated side, right? So the right-hand side is e to the a, e to the b, and I'm just going to write that as e to the natural log, e to the a, e to the b, because e to the power and natural log are inverse functions, and I've just proved the laws of logarithms, so I know that the natural log of a product is the sum of the natural logs. and that's e. So ln of e to the a is e is just a, and ln of e to the b is b, and that's the left-hand side, and we've done it, right? So you see somehow once you've got the corresponding law of logs, you're just deducing the one for exponential functions as a consequence. It's not really a big deal. What about e to the a to the b? Well, for this, we've just got to use the definition of what raising this number to the power b means. It's e to the b natural log of e to the a. That's just the definition of this to the power b here that we've used. And so that's e to, but ln of e to the a is just a, so it's e to the ab. And that's, so again, I'm doing this right-hand side, left-hand side business. So this was the left-hand side, the most complicated side, and I've proved that it equals the right-hand side, and there's my proof. Okay, so great. So we're in great shape. We've done everything I wanted, so all is good. But I mean, it was really good for ln. That was very clean and nice. E to the x being the inverse function was maybe a bit indirect, but you know, I'm just being picky, a bit indirect. But you know, I always have the feeling that e to the x should be easier. The exponential function should really be an easier thing than the log function. I mean, you've always thought exponents are much easier than logs. So this seems a bit turned around, that somehow we've got a nice clean and tidy definition for log, but then we have to kind of go via that to define the exponential function. So, you know, you might be bugged by this. How can we define e to the x more directly? So let's move on to the second approach. So I'm kind of going through a long story fairly rapidly here because it's really just setting the scene for things we're going to be doing. Well, we could try to define e to the x to be the unique solution to the differential equation. And let me see, so we know this differential equation, f prime of x equals f of x with f of 0 equals 1. Right? You know that e to the x's derivative is e to the x and e to the 0 is 1. So you know, since we kind of know this function e to the x that we're trying to give a rigorous mathematical definition of, you know that that differential equation and that initial condition characterizes this function. So this is rather good. You can prove properties like the law of exponents directly. If you took this as the definition, e to the x plus y equals e to the x, e to the y, you can do this quite easily. Indeed, let's see if I can do that. If you let f of x be e to the x plus y over e to the y, so I'm treating y as being constant, x is the variable, there's a perfectly good function of x. What's f prime of x? Well, I've got to this is just a constant. I've got to differentiate this using the chain rule, but the derivative of the inside, that's the inside, is 1. So the derivative is just e to the x plus y over e to the y, which is f of x. And what's f of 0? Well, it's e to the y over e to the y, which is 1. But the unique function solving this differential equation with that initial condition is the function e to the x. So actually f of x is e to the x, which shows that e to the x plus y over e to the y is e to the x, which shows that e to the x plus y is e to the x, e to the y. Okay, so if you take this as your definition of the exponential function, the unique solution of that differential equation satisfying that initial condition, then using that approach to defining it, you can quite quickly get to your laws of exponents and you're in business. But there's a problem. It's easy to see that if there exists a solution to this differential equation, then it's unique. We know that. That's because two functions with the same derivative are equal up to adding a constant. But we haven't proved existence. So maybe you were letting me do this totally happily, but there was a kind of a big gap here. I haven't done anything with this approach. It doesn't make sense. I haven't proved that there exists a solution to that differential equation. If there does, we know it's unique. And so this proof of these laws of exponents, which just used uniqueness, would be totally good. But I haven't proved existence. So that's kind of a problem in this approach, trying to use differential equations to define these functions mathematically. Now, we could go off and we could develop some nice theory about existence of solutions to differential equations, and there is such a theory, but we haven't done that, and it somehow comes much later in history, that point of view. But there's a third approach, which will fix up the second approach as well. So let's just finish by kind of talking about the third approach, because this is really where I wanted to get to, and the big theoretical topic that's really kind of the next stage in the development of calculus. The third approach is to use power series. This is a major theory, and it needs to be developed. Rather carefully at this point. But there's no doubt that Newton already thought in this way. Okay, so Newton, very soon after he had discovered differentiation, integration, fundamental theorem of calculus, and done all this stuff on planetary motion and so on, he would have been thinking about power series, and I'm quite sure he was thinking about functions in terms of power series in exactly this way. And so everything I'm showing you, Newton would have been thinking this way. He would probably have been thinking rather informally in this way, so he might not have had rigorous proofs or definitions of these ideas, but the ideas were certainly things he was using. So what's a power series? Maybe the very first power series that you should know is the geometric series. We've talked about this before, in fact. So that's the infinite series, 1 plus x squared plus x cubed plus ... which you know converges to the number 1 over 1 minus x, providing the absolute value of x is less than 1. So this is something that was really ancient. It was already, for example, Archimedes already used this in his proof of the quadrature formula. If you read through that proof, you would see that this was being used there. Fermat used this in proving Fermat's theorem. We've seen this in the lectures before. So this is something that was predates calculus by a long, long way. That's maybe the first series you come across. In general, a power series is something like a0 plus a1x plus a2x squared a3x cubed for a sequence a0, a1, a2 of real numbers. Let's see if I can give you a shorthand for that, because it's better to write it as an infinite sum. So it's the sum n goes from 0 to infinity a n x to the n, right? So it's a series of powers, power series. Of course, that's an infinite sum, so you have to know what an infinite sum means. And the meaning comes from the notion of limit. You can look at the finite sum as little n goes from 0 to big N, a n x to the n. So that's kind of called a partial sum. And then you take the limit of those partial sums, which are good real numbers, as big N goes to infinity. This may not converge. It depends on what the coefficients, these a0, a1, a2, and so on are, and it depends on what the value of x is. And the x in the real numbers for which it does converge gives the domain of the function f of x. So I'm going to just call this f of x now. So that for those x's, that series converges to some real number, and that's the value f of x of the function defined by the power series. Okay, so I'm just kind of giving you a really quick review of stuff about power series. So all you need to have a power series, right, is this infinite sequence of real numbers. As soon as you have this infinite sequence of real numbers, you get a function defined by that power series. The domain of that function is the set of all x's where that limit exists. Certainly the number x equals 0 is in the domain. It's perfectly possible there are no other real numbers x in the domain of that function. So that would be a very stupid function. Or it could be that every real number x is in the domain, that series converges no matter what x is, and then you would get a function f of x defined on the whole real line. But either way, you get some perfectly good function out from your sequence of real numbers. That's called a power series. And I'm just going to write down kind of the basic fundamental theorem about power series. Given a power series, f of x, as above, there's r, which is either a real number greater than or equal to 0, or maybe capital R could be infinity. And this is called the radius of convergence of the power series. So that this power series converges for all x with absolute value less than r, and doesn't converge for any x with absolute value bigger than r. This then gives you a function on the domain minus r, that open interval. Those are all the x's satisfying that inequality. The function f of x, so on that domain, inside the radius of convergence, f of x is actually differentiable, hence continuous, and the derivative f prime of x is the series summing n goes from 1 to infinity n a n x to the n minus 1. So that guy there, I often call that the term-by-term derivative of the power series, because I've just applied the power rule to each of these a n x to the n's to get n a n x to the n minus 1. Okay, so inside the radius of convergence, the function defined by the power series is differentiable, and the derivative is the term-by-term derivative with this series also converging on that interval minus r. Okay, so this theorem needs a careful proof, but it lets me talk about the radius of convergence of a power series. Perhaps the radius of convergence is infinity, and in which case that power series defines a function with domain the whole real numbers, which is differentiable. Because once it's differentiable once, it's the same theorem, then you can apply it again, and again and again, and you see that this function is infinitely differentiable. So that's pretty much everything I wanted to say. I actually wanted to add in one word, maybe right here. And the word I wanted to add in is the word absolutely. So it doesn't just converge, it converges absolutely. And from your first calculus course, you probably remember that word absolute convergence. So it means it still converges when you put absolute values around the series. That's the technical property that you need to be able to manipulate this power series to maybe rearrange its terms, or we'll be taking products of power series and so on. You need absolute convergence for all of those manipulations to be justified. Okay, so I want to try to finish this story up in the next 5 minutes. So it's worth pointing out that if you have a power series, so you have a function defined by a power series, and it has radius of convergence bigger than 0, it's possible that that power series has a radius of convergence 0 when it's completely pointless and you wouldn't think about it. As soon as the radius of convergence is bigger than 0, you've got some open interval on which this function is differentiable infinitely many times. So actually then you can recover these a's, these coefficients, from the function. Because of course a0 is just the function evaluated at 0. If you plug in 0 here, that means that's a0. And a1 you can recover by taking the derivative of the function. When you differentiate, that drops off, you get a1 plus 2a2x and so on, and if you plug in 0, that gives you a1, and then a2, that's going to be the second derivative evaluated at 0 over 2 factorial. In general, an is going to be the nth derivative at 0 divided by n factorial. So probably that's something you're familiar with. Okay, so if your function is defined by a power series, you can recover the coefficients of that power series by evaluating the derivatives of your functions. For example, f of x equals e to the x. If we could define it by a power series, this would show that all ANs in that power series would be equal to 1. So this suggests, I'm kind of always going a little bit backwards because I already know this function. I'm just trying to discover a good mathematical definition of this function, and I'm going to define the exponential function by a power series. So sort of turning this around with the benefit of hindsight, if you're looking for that power series, you can work out what it is just by using that formula. That tells you what the coefficients in the power series have to be. So this becomes, by definition of the exponential function, all of those coefficients, so not all an equal 1, there's this n factorial in the denominator there, right? So the derivatives of the exponential function, they're all e to the x, and when you plug in 0, you get e to the 0 is 1. So all these an's, so 1 over n factorial. So there's going to be 1 plus x squared over 2 factorial plus x cubed over 3 factorial, x to the 4 over 4 factorial, and so on. Okay, so turning this all around, you think, well, how about I just take that power series and take that as my definition of the function. Note this power series has radius of convergence infinity. So you have to show that that series converges for all x. And from your first calculus course, you probably learned techniques to do that. You would probably use something like the ratio test to check that this series converges. Hence, it gives an infinitely differentiable function with domain, the whole real line, and the derivative of e to the x. Well, that's the term-by-term derivative, and if you do the term-by-term derivative of this series, you get 1. Yeah, that gives you x. That gives you x squared over x cubed over 3 factorial, and so on. So when you differentiate that power series term by term, you get the same power series back again. And what's e to the 0? Well, that's a0 equals 1. This gives a function solving the differential equation from the second approach. So once you have power series, you can use power series to construct functions which solve differential equations. So the second and third approach, they kind of go together. And so this becomes a totally excellent and well set up way to define the exponential function from scratch. So this, I think, is the best way to define the exponential function. For example, this rather mysterious number e, it's just the limit of this series. That's much nicer than the other property we knew. I've just from the original definition of the exponential function as the inverse of the logarithm function. That would have been the property characterizing e, which is much harder to calculate. Whereas just summing this series, you can quite quickly get e to quite a lot of decimal places of accuracy. So this is kind of the punchline of this. Let's go back to that differential equation. There's no doubt Newton was already doing this. You should sort of think about this differential equation as a recipe. As a recursive recipe for computing a power series. Right, so we know that f0 is 1. So that tells us the bottom coefficient, a0 of the power series. And then to get a1, well, a1 is the derivative, f prime of x evaluated at 0. But f prime of x is f of x by the differential equation, this recursive recipe. So that gives you that a1 is 0. Then that gives you a2 is 1 over 2. And so from that differential equation, you see that if there's a power series that would be a solution of that differential equation, has to be this power series. And then you just use the whatever ratio test you need to prove that that series does indeed give you a well-defined function, and lo and behold, that differential equation has produced a good function here. So I think I'm going to stop right now, but I'm going to say more about power series and this idea that a differential equation is really a recursive recipe for calculating a power series, and Newton definitely thought this way. I have written down this formal theorem about power series, which is basically the thing I'm going to use every time I do anything with power series. Probably this theorem was proved quite a bit later. Maybe someone like Cauchy or someone would have been the first person to set this up very carefully and systematically. But the idea of power series is well, the idea of the geometric series is classical. Okay, let's stop for today.